Well, I'm sure everybody in this room has heard about this for one reason or another. Incredible deposit. Found, I don't know, was it 20 odd years ago? Doesn't show much, some data. We had an opportunity, Condor did, to work on a couple of surveys that were flown over Pebble. Here's outline of Pebble West, Pebble East, and on the side here is a result from these images are from a spectrum survey. So I think it was in 2010, Anglo commissioned their proprietary Airborne Geophysics system over Pebble. So that's an active source time domain system, similar to the ones that Adam had, like the Megatem and the Tempest. It's actually closer to the Tempest, but it's a lot more power. And it's also based on a twin-engine Bastler, so that's the standard platform for the big heavyweight system. So they flew the spectrum system, and they also did an orientation Z10 survey over the deposit. Then they came back the following year and did a Z10 survey over a much larger block. And then, of course, things got messy. We got release from Anglo to show the data I'll be showing you, but then they backed out of the thing and everything, headed south, as they say, or north. And, Anglo left, Rio Tinto got rid of their, I guess it was 20% of Northern Dynasty. So all the majors sort of headed for the door at the same time, but we were left with a bunch of these show rights for these data. Geotech had some show rights, but I don't know if these were ever shown in the audience up here. It was just one of those things that it's been circulated probably 3 or 4 years ago inside geophysical shows, but it never really got much other exposure. So I thought it'd be nice to sort of show you what a really big honking porphyry system, because it does show some really, really interesting characters. So we've got the resistivity, or a lake time resistivity called time constant on the right, and then the TMI sitting over on the left. And Eric Anderson, known to some of you, he did research on this, was analyzing the aeromagnetic signature of not only Pebble, but the whole kind of arc that Pebble sits in. And there was quite a bit of legacy USGS work at Pebble, which came out in dribs and drabs. I don't know, but there's Karen Kelly's wonderful edition of Econ Geology, where a lot of stuff was put together. Some of the geophysics was there, but unfortunately the USGS only published on the work that they did, which was sort of MT, the aeromag analysis. They never actually had access to any of the airborne data sets, which were pretty interesting, and normally the sorts of things that in industry get put up front. So the USGS work was good, but without this other information, the story was incomplete. And so this is maybe the second part, build on to that. So I'd certainly refer you to that Econ Geology special issue that has on the geochemistry and the geology. Great resource, but it was missing pieces like this. So, location, it's big even by Alaskan standards. It's in another one of these pretty interesting accreted terrains. I saw an animation recently of how things all folded together up in the Yukon and Alaska. And it's some amazing GIS chronal package where they can actually now have all the plates move around in a little animation story and sort of get an idea of how these things built up over time. And it's very, very, very interesting. But saying, okay, Pebble's where it is. Here's the regional geology. I'm sure some of you in the room know this far better than I, but I included this slide just to show that, okay, we've got a lot of volcanic rocks it's hosted in, and there's some, also some, I think some anorthosites that are very magnetic. That's the large magnetic body right here. Catches attention, and there is some, that does form some sort of model in its own right, that I know some companies have chased elsewhere, I think further to the west of Pebble. But the key thing about Pebble, ultimately, when you stare at it enough, is a bit like Casino, is that the deposit itself is a relative low, but there's a very, I think, genetically significant magnetic anomaly adjacent to it that probably is related to it. And the proximity of Pebble to that and that belt is pretty important. That the two are related, and I think Eric certainly thought so. But you know, often, as I said earlier, when everything's taking place at 1.5 to 2 kilometers, it's often quite difficult to have the exact information you need to geology map. Outline of the Pebble West and Pebble East with some of the drilling. Most of these are because that's all you can get these days, are out of 43-101s. The annoying thing is, if you do sleuth 43-101s, you see 5 of them coming out in 6 years, you really have to look at all of them, because the slimes will actually change images, and they'll delete things. And so you may actually find in the third 43-101, even though 95% of it is common, something has been put in that isn't in the others, and then it's deleted. I don't know why. Sometimes the same companies will be doing those. So you spend, in this case, I think there's about 8 43-101s that spanned when they started producing these documents. This part didn't change very much, but some of the other ones did. And of course, this was one of these, you know, God bless it, projects we had to work in imperial units. But it wasn't as bad as the one in the Honduras, where we worked in feet for X and Y and meters in Z. Yes, anyways, at least there's a strange projection, but we were able to figure it out, and but you have to keep track of your products, because our software, our inversion software, doesn't work in feet. We have to convert everything from feet into metric and back again and rotate it, and it's a very time-consuming and very easy place to make errors. And so this was not, it was a neat job, but it was very taxing. So lots of the large batholiths to the west and batholithic rocks down in here. I mean, certainly the magnetics and the EM highlight those fairly well. They had a number of zones, 38, 52, 37, I don't know what, in a 43-101 document. They might get a paragraph tops, so you really don't know what the geology is. They've probably taken some samples, they might have done a few drill holes. But to my understanding, the main story remained up at Pebble, Pebble West, and Pebble East is where the major resources were. Of course, there's surface mapping for Pebble West, but Pebble East, because of its depth, you can see in the next section, is important. And so we spent a lot of time with the geophysical data and the inversions, trying to see how we could map, whether we could map effectively the change from Pebble West on the left-hand side, which is relatively shallow, but unfortunately doesn't carry the grades or tons that Pebble East does, down to this large block, down to the down drop block. With this, also, what's important in the geophysical story, it's a bit like Abraham's permafrost, is that, you know, you got this big wedge, and you say, well, okay, that's a nuisance because it puts distance between us and mineralization. But geophysically, it has its own set of characteristics too, and so we have to cope with things like that to actually get through them if we have a chance of seeing something at that sort of depth. And it wasn't so bad. I think we did a reasonable job. And you know, galactic class resources here, over 100 million ounces of gold, I think is listed on the thing. I understand there was 2 campaigns of IP. The first one was a fairly long program, I guess done, I would call it incrementally, by Cominco. So after the initial discovery, they probably did the work around Pebble itself, and then eventually they moved down south to cover their complete land package. Then my understanding is a more modern survey was done probably in a much shorter time frame, but those results were never released publicly. And so even though we had access to the airborne data, we never were asked to do anything with the IP. So these are out of one of the 43 101s. They kept repeating this time and time again, but they don't really give you much information about the A spacing, dipole spacing. They just say, right, this is it. And I don't really blame the guys that write the 43 101s because probably the client hasn't really given them that information. So also they had this penchant for displaying the resistivity in log space as opposed to linear space. But anyways, conductive is the more purpley colors, and the white color at the top is more resistive. So what does it say? Well, there's obviously, on the chargeability, it's not surprising that Pebble East doesn't show much because it's very deep, and so even with the modern, say, Titan or DS or Sidvisor system, it would probably be very hard to see down the sort of depths that is. But certainly there's character, and we'll see an enlargement, there's character around Pebble West. It's kind of suggestive we may have some sort of pyrite alteration just around the edge of the deposit, but there's also some features that seem to go inboard of it. There's some extensions up to the north, and then it seems to terminate, and then there's a large feature, it seems down here, that doesn't look that much different. It's not apparently mineralized, and then there's these blobby bits. Some of them associated with some of the showings, that might be how they got to them, was looking at the IP data. So, weak one here, what they call 65 on this southeastern branch. So the IP certainly showed there's a big sulfide system associated with this, but the localization of Pebble within that data is not, to me, at first principles, all that obvious. Now the resistivity is a little more, call it, compelling, because you've got a fairly strong anomaly sitting on the north side of Pebble West. Again, the data would not have interrogated to the depth of Pebble East, it's just too deep. You would have to have designed it explicitly to do that, and I think that's where the USGS work, it was a combination of work that they did, and I think the Rio Tinto, when they were operating it, they did MT, I think with the purpose of trying to get the depth of investigation to see something over Pebble East. But you can see here that the conductivity feature is much more restricted around Pebble, and there really isn't much, which was probably fairly disappointing for them. These ended up being pretty lean, pretty skinny. There's a little bit more character here, but then the chargeability associated with this wasn't all that great. So it looks like the resistivity has actually got more of a, drill here type of, or go look here type of expression. My understanding is, and we see some of this character to the north, these conductive zones, is sections of large, thick conductive superficial material. Outwash, clays. It's not actually alteration or a bedrock source, it's superficial. I don't know much more about it. It's sort of the people that told me about it says, no, it's nothing, it's just this stuff you don't want to know about. There's kind of an enlargement with some notes that were in the 43, I recall, so you can see the chargeability on top, and they note, yes, the strong response along the west side of Pebble, and it could be, if there was a companion wraparound on the east side of Pebble West, that got downthrown with Pebble East. I don't know, but it's certainly not perfect, but it does give you the feeling that there is a wraparound, but it seems to be truncated on the eastern side. This high here is, we can see again, is pretty obvious. Suggestive in the center of the porphyry, Pebble West, it's more resistive, which is often what we associate with the potassic core, that potentially could be a resistive body compared with a slightly more conductive one in an annulus shape that also corresponds with potentially this sulfide halo. There's a snapshot of the spectrum system. Great colors and a good system. The Z10 system, Z10 system looks like this. It looks like a Digem system that lost its way because the bird is way down here. It's not sort of up in here. And that's because they don't want to have noise from being in the a natural field system using natural occurring AFMAG signals. The helicopter itself can actually contaminate the receiver here. And then on the ground, there's 2 other base stations that they mount, and then it does record a magnetics data with a sensor sitting approximately there. So one of the things about the Z10 is that and Adam's talked about it a fair bit, it's just one of the aspects of these technologies is that the higher off the ground for active source systems, whether frequency or time domain, the higher off the ground you are, the less penetration ultimately in the earth you get, because the signal does attenuate even going through air. So if you fly, particularly say a DGM system, which is the lowest powered of the bunch, if you fly it at 200 meters, you're not going to be getting 100 meters into the earth. You're going to be getting 30 or something like that. And so you have to be very conscious of this when you look at the data, and that's one of the things that if you download some of these data sets, you should try and check what the radar altimeter is and look for areas where that system is probably too high to get reliable information. The problem is you still get signal, but that signal's not coming from the earth, it's coming from air. So you say, boy, that's really resistive there. That's because you're off the deck too far. So when that information is in the data, you just have to look at your radar altimeter and you can grid that up and warm yourself. The time domain systems are a little better because they carry more punch. You can see they've tucked the birds in. There's the mag sensor there. And there's the EM sensor there. Then they've got their independent cables, and so they drape them sitting back about 120 meters from the aircraft. The Z10 system, though, because it's using naturally occurring fields, can actually fly much higher. So it can do what we call, in rugged terrain, a loose drape and still get usable signal. So it has some real advantages in Porphyry areas where, from a safety point of view, pilots would much rather be up high. So the shot on the left, Adam has already shown us. But this is something about what the Z10 measures. Lightning strikes in equatorial areas are the dominant energy source for this, and so it actually has seasonal variability in terms of signal strength and when the system can be operated, but it can get up to and over depths of around 2 kilometers in the right situation where it tends to be resistive, works quite well. It's sort of the bandwidth that the system operates. So all this energy, this profile here, is out there, increasing in amplitude and lower frequencies, and the Z10 system basically listens from about 20 hertz up to about 700 hertz and gives rise to, and then there's other things, power line harmonics, there's VLF signals farther up, but that is free energy if you know how to tap into it, which the system does. So that's what this is the story that Anglo first set up. They had the black lines were their spectrum in-house system that they ran, and then I asked the people at Geotech, why in God's green earth did they fly lines that were oblique to the spectrum ones? I mean, who would have thought that was a good idea? Anyways, it was miscommunication between, it's like, remember that story of Lockheed and NASA when Lockheed was working in feet and NASA worked in meters, and that spaceship went into the atmosphere in Mars and burned up. Well, nobody burned up here, but these things happen. So it made it very difficult in doing comparison things, which is exactly what the client wanted to do. Because none of these lines could you line them up and say you're going over the same piece of geology? It's oblique, and you had to sort of like, okay, we got to look at a bunch of lines and try and figure the story out. So the test with the Z10 was done. In the following year, they did a production. This is the production block. So there's the blue is the original spectrum, and then they did a full court press with Z10 the following year. So it was 09, and then in 10 they came back with the Z10 and did the whole area. So they got themselves lots of data. Look at the mag again on the left. Some of their prospects. There was certainly some high mag associated with some of these, remember, chargeability anomalies in here as well. So, but Pebble itself, you say, well, if I want an analog to Pebble, maybe I need to be near some moderately high magnetics, but not really hugely high. And then the white dashed line here is the IP outline. So the thing is, the people that did most of this work away from Pebble, including the people I worked for, they didn't know anything about it. I mean, that was all legacy stuff done by people 10, 15 years before. So really the records were probably pretty incomplete as to what they thought about things and why they did things. You know, when Anglo came in, or Rio Tinto, they really focused on the main game. I don't know that Anglo did any airborne. It was, RT, but Anglo certainly tried to crack the nut open and see if they could find some shallower, similar resources to certain what Pebble East is. Back to these, and I'll just say comment that these are big intrusive bodies. They show up in the geology pretty well, and so you're not really, in a way, adding much to the story other than showing that you can map them independently with the Airborne Geophysics survey. Then these conductive sediments, as I described them, they certainly show up pretty prominently in the Z10 data. You also get some of the character, the stronger parts up in the north. That's the mag, so there's something going on correlative up in there, but that definitely, you know, I don't think if you had a pebble underneath this, you would see it. But remember the little resistivity conductive zone with the IP? Now with the Z10, we're actually, the time constant, we're seeing a much larger feature in here from the airborne. So that's kind of, this is the time constants coming from the spectrum, I'm sorry. But that's expanded that conductive area. It's wrapping over the top of Pebble East, and it's actually seeming to come out down at the junction of Pebble East and West on the south side. So there's a growing conductive anomaly associated with Pebble that really the IP didn't show up particularly well, which is pretty interesting. Here's a zoom in on the mag. We've got a 3D model stuck underneath 2D grid, and you can see the Pebble West is on this plateau. Pebble East is really pretty indeterminate. There's kind of the green blob here, but this is that Anorthosite down to the south. It's the big boomer. That's with the 3D model. This is actually I think it's their 0.6 copper cutoff. So you can see why they have to have Pebble East for the story. There's a zone here of mineralization. There's the outline of west and east, but here in the 3D model, we actually have the ore blocks stuck in next to the magnetic body. And there's no real question that the Pebble system itself is non-magnetic, but it is in close proximity to a fairly magnetic body. And that's the mag micro-leveled. We tried to really, Eric was very excited about the magnetic response within Pebble, but I said, well, Eric, really the story is that what's beside Pebble is important. Pebble itself is pretty tame. There's the time constant again with the outline of the deposit, so we were pretty impressed with what we saw, this kind of emerging sort of semi-annulus type response in the EM. Spectrum Dec Slices. This is at 550 meters. Now you might get excited with the one on the left and say, hey, maybe it's seeing Pebble East. We think this is that wedge of tertiary sitting over top. It's conductive. It's a clastic, volcanoclastic sediment, volcanic mix, and I think that's probably what that response is coming from. That's not even deep enough to be seeing Pebble East, but it is within that wedge. So you just have to appreciate these sorts of things happen. There's the Z10 at almost the same depth slice, and that's probably the contact with that wedge on the east side, so Pebble West, Pebble East, and then this would be an axis of contact. It appears to be conductive, but it's probably a major structure, and that's probably the bounding fault between west and east that we're picking up there. Not mineralization, but the structure itself. So that was a comparison. I went back and just showed the resistivity again. Fairly small feature, fairly small conductive feature up there, but much larger, much more prominent. So the airborne results really brought out a story that the ground geophysics didn't show so much of. Here's some sections of inversions and geology. So we've got these block models. That's the low grade and the higher grade in blue. And so you're seeing them in section, and then this DXF is actually sticking out. That's why that little rind is hanging around it. And then I put those up into the conductivity model. So that part where we saw that depth at 500 meters that was conductive, that's coming from here, and that's where that wedge of plastic volcanic sediments is sitting. The Pebble deposit itself is actually below 1 kilometer at that point. So we don't think we touched it, even with the Z10 data. Because it's too conductive, we weren't seeing below it. Z10 does run out of puff. It's really good, like if it's permafrost, it can go down over 2 kilometers, but you hit something conductive, that basically stops it in its tracks. But like with the other systems, it's not as I don't want to say bad as Digium. It sees deeper than a time domain system, but not that much more. Here's some comparisons between a version of the spectrum data and the ore block model on the top. So we call it the layered earth inversion LEI. And then the Z10 result shows a similar feature, but it's softened. It doesn't have the spatial resolution that the time domain data does. So Pebble West is basically that conductive slab near surface. Both of them kind of map it. And then this sort of has this gentle sort of roll off. This has a little bit more of an abrupt drop. And there's the actual, that's what the block model looked like in that section. So reasonably suggestive of what was going on with the geology, with things getting deeper. Obviously past this structure here, things got a lot deeper, a lot faster. And some of the images seem to highlight that a bit better on different sections, so we don't see total consistency. Here's one of those, this is a 3D model where the ore body is in blue, and this is the EM conductivity model and the sections that it's come from. So this is Pebble East and Pebble West. So we can certainly see that there's a thin, albeit important, and shallow part that's represented by the western part of the deposit, but the eastern part that holds the big goodies down in here is a bit deep. So, and that's that. I think that's that wedge of conductive material sitting over there. So, yeah. So the magnetics data shows us a relative low over the deposit, possibly due to destruction of the magnetite during the formation of the system. But importantly, there's a proximal magnetic high adjacent to the deposit. It could be the feeder, sister, some parent intrusive associated with it. I don't know if the mineral chemistry, if it's really that's been studied, because it's a geophysical observation that was done fairly late in the piece, at a time when I think the owners and operators were not really interested in academic analysis as to where it came from. But I think if somebody did an assessment and looked at the rocks around Pebble and then went to look at those more mafic rocks to the west, you may well find there's some affinity between the two. The EM surveys are pretty good at mapping both in a 2D sense as well as in a 3D character of the deposit. I think the IP resistivity, in the earlier results that we see aren't really, the chargeability is interesting, and the resistivity is a bit of a teaser. Maybe the subsequent, the last survey that's remained proprietary is stunning. I don't know. Nobody's ever commented to me about it, and I haven't seen those results. So that's what we saw at Pebble.